Hello again, everybody. Welcome back to my home. Again, this is a different format than GoToMeeting. There's no transcripts and there's no microphone. This I will upload to YouTube. Then I'll put a YouTube link on Noodle. I think the last video I said something. We're having difficulty with GoToMeeting. That should be fixed tonight. But we'll see how this works. This is actually the fourth time I've done this video. And none of which are really, I'm not really happy with any of them because this is truly very, very highly theoretical section. And as such, I really do encourage you to go elsewhere to get a different perspective, particularly, just because of what's going on, I'm going to de-accentuate this. In fact, here we go, it's your homework. There's only 3 problems on page 206. 177, number 188, and number 189. That's page 206, numbers 177, 188, 189. There's only 3 homework problems, and because of what's going on, I'm not so sure we're even going to, this is even going to make the exam. We'll see. But so this is part 2 of section 2.5, and again, it's very theoretical. It's precise definition. Those of you who are mathematicians going on to math majors, for example, you really want to understand what we're talking about here because you're going to be doing this a lot throughout your time. And so we're going to put the definition up again. We had it on the last one. Do an example, and then really I'm just briefly going to talk about those 4. And then let's finish chapter 2, actually. Again, type in formal definition of a limit. There are so many videos, and they're interesting stuff. This is conducive to movement. Actually, there's an applet in the book, right? I don't know what page it's on. Probably on page like 190 or something. And you can move epsilon and delta. And this is a hard one to teach in a stagnant environment, in other words. Okay, so I would encourage you to do that. Formal definition of a limit, or what we're calling precise. So, definition. How do you start the formal definition? Oh yes, definition. So this is a definition. Let f be a function. Be defined. Come on. Find on some open interval. On an open interval. Containing a real number a. Okay, so f is a function. Then, this is the definition part. Definition, the limit as x approaches a of f at x equals L. That's a definition where a is a real number. X can't be a, by the way. L is a real number. Containing a and x and a are not the same thing. That's the definition. If we assume 0 is less than the absolute value, we assume that delta. We assume that x is within delta of a. I'm going to write those words down. We assume that if that's true, then I'm getting low. Then this is true. Not even. F at x minus L is less than epsilon. For every single epsilon out there, there exists a delta. There's a delta. There exists a, I'm going to rewrite. Yeah, let's do this over here. There exists a delta. I have some words written down here. I'm going to share them with you. This is all, again, theoretical, and we talked back and forth. This 4th video I made here. Here we go. If, for every epsilon greater than 0, if this is true, 0, less than, I do that all the time. There exists a delta greater than 0 such that, I wrote that sentence up the other day. for every epsilon, there exists a delta greater than 2, such that if this is true, 0 less than x minus a less than delta, then this is true. F at x minus L less than epsilon. All right. Assume, and that's what we want to get. What we're saying here is if, how does this go? If x is within a of delta, is, let's put it the way exactly, is closer than delta to a. The delta's a number. That's what that says. I mean, we're trying to get this number, x, getting as close and close to a, and then this is f at x is closer than epsilon to L. Bah! Picture, function, that's a, this is f at a. What we're trying to do is have a epsilon, that'd be plus f at a plus epsilon, f at a minus epsilon, delta, a minus delta, a plus delta. And again, do the applets. Oh boy, I don't know if you'll see the light of day here either. But so we want to squeeze it. We're assuming that that is true, and then we're going to show that there is that it works for every single epsilon. Okay, enough. I didn't mean to do that actually. Yeah, let's. Here's the convoluted part, and the examples from this, and I'm going to do specifically example 2.40. 2.40. Show. Oh boy, I forget what it is. Equals 3. 2x plus 1. 2x. Oh, yeah, show. Limit. X goes to 2x plus 1 equals 3. X goes negative 3. Right. Negative 1, negative 3. Oh man, I really screwed this up. This is, oh, that's because it's the wrong example. Plus 1, as x goes to negative 1, negative 3. Oh, I'm sorry about that. Okay, that's the example. And so what we're going to do, how we're going to do this? Well, let epsilon be greater than 0, some number, assume that, and then choose delta. Choose delta equals, oh, you know what, I think I'll choose epsilon over 4. Huh? Why? Because we assume x minus negative 1 is less than delta. We assume this. And so this is x plus 1, or x plus 1 is less than delta. And now we want to make it look like f at x minus L. We want f at x minus the limit L. Somehow, we want to manipulate this. So, there it is. Just notice, how about we do this? Is 4x plus 1 minus negative 3. That's what we're looking. That's what we're looking for, and I want to change it into that. 4x minus 4x plus 1 minus negative 3 is 4x plus 4, which is 4 times x plus 1. That we're assuming, which is less than, I guess, 4 delta. How's that? And then, so let epsilon, choose delta to be epsilon over 4. There we go. Delta, epsilon over 4. Because we're going to get to this point right here, and we're going to make that, and then that's going to be epsilon, and right there's the less sign. So that's how the proof works. Okay. Let's move on. Please, again, I would highly, highly recommend getting some other perspectives. They'll have things moving. You know how technology works. They'll have colorful, dynamic displays Not specifically familiar with anyone. I know Khan Academy quite well. I actually was going to be Khan Academy when we were at Penn State. It's a long story. And here, in short, Khan Academy took the human out of it. Penn State tried that with me. They said, Brad, we're going to put you on the web all over the place. But they videoed, just like right now, they videotaped me. And it didn't work. You know, Khan Academy essentially took the human being out of it and just did it on an iPad. That's where we made our mistake. Otherwise, you know, I probably wouldn't be here. I'd be a billionaire. What are we on? Oh, just notes. Notes. Let's finish this section. Notes. They're non-linear limits. Let's just do something like a quadratic, for example. A quadratic, f of x equals x squared, the limit as x goes to like 2, and show that. They get really intensely difficult. This is much more complex than the linear one we just did, than that one. So, and again, I would encourage you to go, there's an applet in here, actually, than the one, example 240. So I just know that they're there, you know, and almost every textbook does an x squared. They don't bother with, man, you go to like x cubed and everything, the algebras, you will, as long as you continue in mathematics. All right, got 240, and just, again, these are notes. There are infinite limits. Where are we at? Oh, one-sided limits, infinite limits, is that where we're going? Oh, there's something called, this is actually a note, triangle inequality. For any two numbers A and B. This is only because we use the formal definition of limits to prove this, and it's very important in mathematics. That's a triangle inequality. Period. Those of you who are going to analysis, actually calculus too, we use that in calc too. And so then there's, you know, just that's it. It's a note. One-sided limits, I'm just drawing pictures. You know, the formal definition for work with stuff like this is, say, oh yeah, absolute value of x over x, something like that, and 0 is undefined. But if you come from x goes to 0 from the left, the limit would be negative 1. If you go from the limit as x goes to 0 from the right, it would be 1. But the limit at wherever it is, at 0 does not exist. That's by the way, I'm hitting you with that in the quiz, because a lot of you got number whatever wrong. It does not exist. You just say do not exist. But they're one-sided ones too. Infinite limits. There's a whole definition of this. We'll get back to it. Actually, we're going to get back to this. But just for us, 1 over x squared, the limit as x goes to 0, would look like that.